Okay, so, nice, so this dp is 0, so therefore this guy should be 0. And by solving this equation, I can find this equation, or this is by integrating this equation, I can find the equation for that surface, which is the relationship between z and y. Make sense? So that's the application of this equation, finding the equation of the free surface. So please write it down because we are going to use this. Also, it's available in your slides. Now we want to solve this equation problem. Okay, so what we have in this problem is the cross section of the fuel tank of an experimental vehicle is shown in this figure. The rectangular tank is vented to the atmosphere, and the pressure transducer is located at its side as illustrated. This is where the pressure transducer is. So it's when the tank is not moving, the free surface is in horizontal orientation, and the transducer is 0.5 feet below that horizontal surface. So when we say it is vented, means that the pressure of air inside the tank is the atmospheric pressure. And during the testing of the vehicle, the tank is subjected to be a constant linear acceleration. So we just have a sub y, a sub z is 0. Okay, so determine an expression relates a sub y, the pressure in pound per square feet at the transducer for a fuel with specific gravity of 0.65. So let me write down the equations that we are going to use here before getting started with this equation. With this problem. So let me just write down the equations here. Okay, so we have this equation, dP is partial P, partial Y, dy plus partial P, partial V, dz. And by plugging the right hand side of the equation for partial P, partial Y, and partial P, partial Z, we have dP is minus rho a sub y dy minus rho u plus az dz. And for the free surface, or the free surface, as well as constant pressure surfaces, dP is equal to 0. So therefore, we have this relationship as we can find it here, dz dy. We can continue that over here. Minus rho a y dy is equal to rho g plus az dz. So therefore, dz dy is going to be, the rows are gone, ay g plus, excuse me, ay divided by d plus az. This is what we have. Okay, the first thing that we need to find for this problem is determine a pressure that relates AY and the pressure at the transducer for a pure gravity, specific gravity of 165. So let me just going to this is what we have as a tank. And this is the vent, this is the transducer. This is the free surface of the water inside the tank before motion. And after the motion, as shown with the dashed line, this is the shape of the surface, or the orientation of the free surface of the fluid. So if I want to apply this equation, so again, this is the y-axis. This is the z. So a sub y is given. A sub z is 0. So what do we have here based on this equation? dz dy is minus ay g plus az. The az is 0, so we just have minus ay over g. Okay, how can I relate the acceleration to the position of the transducer as mentioned in the problem? An expression that relates the pressure relates AY and the pressure at the transducer for a field of some specific gravity of 0.65. How can I find the pressure here when its tank is moving? Over here.
The distance from, in essence, the dotted line there, where your pressure is 0 times
Here, the pressure, the gauge pressure is 0, that's correct.
so pretty much that distance times
You
the,
mean this distance?
yeah,
Okay, so the problem is how can I find this distance? I call it, for example, delta, correct?
Yeah.
So the pressure here, the pressure, if I call it transducer, the pressure of transducer is going to be gamma delta, is that correct?
Yeah.
Okay, so how can I find delta? Using this dz/dy.
Solve for DZ.
What's that?
Solve for DZ.
Solve for dz, okay. How much is dy here? This is dz for this location, and dy is this guy. dz dy actually gives us the slope of the line. dz dy gives us the slope of the line for the free